So last time we took a look at this animation of taking a random walk in 4D where our random walkers can move in the X, Y, Z, or color dimensions. And while this is a neat way to visualize this, it's kind of difficult to actually study the random walk in 4D here. For example, one of the questions we would want to answer is, are you guaranteed to return home back to the origin as a 4D random walker, or is this another transient random walk, the way a 3D random walk is? So in order to test that, we have to have many random walkers, and we have to be able to calculate their distance from the origin. And while this color is a nice representation of movement in the fourth dimension, it's not really a distance. At least it doesn't map onto the X, Y, and Z spatial dimensions we have here. So in order to test this question of whether this is a transient or recurrent walk, I've set up a new test code here where we're going to work with some four-dimensional vectors. Now, VPython does not have, by default, an object called a four-dimensional vector. It's for animation, so it stops vectors at 3 dimensions, which is good for most applications. But here we need to define a four-dimensional vector. And this has actually inspired me to, in a future video, create a library of a class where you can have vectors of arbitrary dimensions. So you can look for that coming out in the future. But for right now, we're just going to define a four-dimensional vector. So we're using Python's class feature to define a new type of object. If you're not familiar with how classes work, check out the video in the description below about Python classes. You can go watch that and come back, and you should know just about everything you need to know moving forward. When you're working with a class in VPython, you have to first use this init function to tell Python what it is that the user is going to be specifying. So we need 4 coordinates, and the convention for 4 dimensions is to start numbering them at 0. That's not just a programming thing, that's also a special relativity thing. So here we've got coordinate 0, coordinate 1, coordinate 2, coordinate 3. So these are our 4 coordinates. We're just going to assign those to this object. Let's talk about these other functions in a minute. Down here we've got the same kind of loop we had before. We've got 200 random walkers. We're going to create for each of them a 4-dimensional vector and a logical variable to check for whether they return home. This is the same way we've done this for all our other random walks beforehand. So we are familiar with this at this point. And we're also graphing all of them so that we get a cool animation along the way. Down here we've got the loop for our random walk. Just like before, we're going to be taking 10,000 steps. We're going to be checking for whether they reach 0.1 of the origin. Now, in order to give them a step in a random direction, I need to be able to add 4-dimensional vectors, right? I need to be able to add the 0 component, the 1 component, the 2 component, the 3 component. And VPython won't do that if I just say walkers of I plus direction. I need to define an addition function, and that's what we've got up here. We're defining that within the class. So we have the original, we got the original 4-dimensional vector and another 4-dimensional vector. And so basically what we're doing is we're taking the 0 components and adding those together. We're adding the first components, adding those together, adding together the second components, adding together the third components. And that's the thing that we're returning. We're returning a new vector 4, a new 4-dimensional vector that has those components. Now what we're doing with that new 4-dimensional vector is we're using it here to overwrite the previous 4-dimensional vector. So this is the old value here. We're going to add direction to it, and then we're going to save it in the new, as the new value here. And then I need to be able to check for whether these folks are close enough to home. So I have to be able to calculate its magnitude. So I can't use the old mag function because the default mag function in VPython assumes you're working with a 3-dimensional vector. So I have to define my own magnitude function. Fortunately, that's pretty easy. The magnitude works the same way in any number of dimensions. The Pythagorean theorem really is a wonderful thing because it extends to any number of dimensions. You just take square root of each of the vector components squared and add those together, all within the square root. So we're taking the magnitude here. So if I wanted to make a 5-dimensional random walk, I don't think I'll need to do that after this video, but if you really wanted to, you would just add on an x4 to everything, and you would have a 5-dimensional random walk. So here we're checking the magnitude, And just like before, we're counting the number that returned home and presenting that as a percentage of the total. So let's hit Control 2, see what happens with our 200 random walkers here. Oh, this one almost got to home at the end. We should have let it run a little bit longer. As you could see in the animation, we don't get a lot of folks returning home. This one came close here, but we got a total of 17% of our random walkers returning home. That is about half of what we got for 3D. So I think we can pretty safely conclude from this that a 4-dimensional random walk is going to be a transient random walk. In fact, that makes sense, right? Because it's higher dimensions, there's more space to wander around in. So that is currently all I have had planned for this series. Thank you for watching it through, what is this, 12, 13 episodes? If you have other things you would like to try out for a random walk, either let me know in the comments below or feel free to take any of these codes. They're available in the descriptions of the videos of this series and see what you can find out about them. You know, see what neat scenarios you can come up with, what neat ways there are to tweak them. I'm going to continue to sit on this for a little bit, see if there's anything else that I think of, but I think we'll call this chapter closed for right now. Thank you so much for watching. I will see you next time. Bye-bye.